Let's see how we can use the measured and tabulated delta H's of formation to calculate the delta H for any other reaction. As an example, let's look at the combustion of methane gas. Combustion reactions are reactions which combine oxygen with a substance to form CO2 gas and water as a liquid. The balanced reaction for the combustion of methane gas is shown here. Because this reaction is balanced, there's the same amount of carbon on both sides of the equation, the same amount of hydrogen on both sides of the equation, and the same amount of oxygen on both sides of the equation. So if I take the reactants apart into their elements and reassemble those elements to form the products, I will have no elements left over because balanced reactions have atom conservation. When I take the reactants apart into their elements, I'm doing the formation reaction in reverse, and therefore the delta H for this reaction will be the opposite of the delta H of formation for methane gas, because I have taken methane gas apart instead of putting it back together. Notice that oxygen is already the most stable state of oxygen, so if I take oxygen apart into its elements, I don't do anything at all, and therefore the delta H of formation of oxygen gas is 0. The delta H of formation for any element in its most stable state will be equal to 0. Now that I've disassembled the reactants into their elements, I can take these elements and recombine them to form the products of my reaction. So I take my carbon graphite and 1 mole of my oxygen gas to form CO2. I take my 2 moles of hydrogen gas and 1 mole of oxygen to form 2 moles of water as a liquid. The reaction that I have written for forming CO2 gas is just the formation reaction for CO2, and so the delta H for this reaction is simply equal to the delta H of formation for the CO2. However, the reaction that I've written to form the 2 moles of water is the delta H of formation for water done twice, and therefore I will get twice as much energy as I would if I formed 1 mole, and so the delta H for this reaction is 2 times the delta H of formation of 1 mole of water as a liquid. The net result of taking the reactants apart to form the elements and then putting those elements back together to form products is the reaction that I'm interested in. Because delta H is a state function, it doesn't matter if I do this in 4 steps or if I do it in 1 step, the delta H will always be the same. So I can add up the result of the 4 steps to get the result of the single step reaction that I'm interested in. And so the delta H of reaction for the combustion of methane is equal to minus the delta H of formation for methane, because I'm taking methane apart, minus the delta H of formation of 2 moles of oxygen, because I'm taking the oxygen apart, plus the delta H of formation of CO2, because I'm using the oxygen and the carbon to form CO2, plus 2 times the delta H of formation of water, because I'm using the hydrogen gas and the oxygen to form 2 moles of water. Notice that the reaction delta H is made up of the opposite of the delta H's of formation for the reactants and the positive of the delta H of formation for the products. In addition, we must take into account the stoichiometric coefficient in front of each of the reactants or products when we do this sum. I can summarize this into one simple mathematical statement if I define the stoichiometric coefficient for reactants to be negative and for products to be positive. Then the delta H of reaction will be equal to the sum of the stoichiometric coefficient times the delta H of formation for that substance. Now, as long as I have the delta H of formation of every component in my reaction, I can find the delta H of reaction. And this is why measuring the delta H of formation for substances provides us with a good set of reactions from which we can find the delta H of any other reaction that we might be interested in.